Hi everyone, our team has done some incredible work building a machine learning model which will predict the probability of survival following ICU care, and we are excited to share it with you today. First, we'll cover the amazing team that put this work together. Moving to a high-level overview and summary of our findings, then we dive deep into the data, the exploration, and the modeling. Lastly, we'll review insights and deliverables. Shay is going to cover the data and processing, Ravinder is going to talk about exploration, and Ipong is going to review modeling. And I'll bookend us with the summary as well as the insights. But don't let any of the titles below our names fool you. We all worked throughout the entire data science pipeline, from acquisition to modeling and deliverables. Over the next few minutes, we will uncover the work that brought us nearly 7% better performing results than current models used in hospitals and ICUs all around the world today. We'll show you patient trends that we uncovered to improve upon those models. And finally, if you look at the chart on the right, those are the capacity and occupancy numbers for ICUs in Houston right now. Like a previous group mentioned, covering all things COVID, in situations of 98% capacity, this work would give clarity on patient risk factors and manage patient movement for care. Now, Shay is going to go through the data.
Thanks, Chase. When we started this project, we had some really interesting questions we wanted answered. In order to answer those questions, we needed data. Luckily for us, MIT has an open source project which contains data from 200 hospitals across 8 different countries. This data is information about that critical first 24 hours of a patient's time within the ICU. In addition to this patient data, we're also provided with predictions for each patient on their chances of survival. This prediction is made with the Apache 2 model, which has been used in hospitals since 1992. What's great about having these predictions is that we can test our own predictions against them, which will let us know if our models are performing above the model that is being used in hospitals today. Our data contains about 91,000 patients. For each patient, there's 185 variables. These variables are basic information like age, weight, and gender, but also includes measurements of the patient's vitals, such as heart rate, blood pressure, and pH level. One of our main challenges in this project was working through the many measurements we have and identifying the patterns and trends driving if a patient would survive in the ICU. Which raised our next big question. What is the distribution in our dataset of those who survived versus those who did not? Well, we found that 91% of the patients in our dataset survived, while unfortunately 9% did not. While 91% survival rate is a great thing, it's unfortunately not so great for our modeling. This is called an imbalanced dataset, since the thing that we are attempting to predict is heavily skewed towards one side and means our prediction will apply much more significance towards the 91% of the patients who survived. We had to keep this imbalance in mind while we were working through our data, especially while handling the missing values in our dataset. Let's take a look at that missing data. When we first got our hands on our data, we were surprised to find that it was missing 33% of its values. In order to maintain the ability to use the patient data, even if some of it was missing, we needed to fill in these values with averages so we didn't lose too much of our data. However, during this process, we had to pay special attention to the imbalance in the data since we didn't want to accidentally lose too much that was telling us about who was or wasn't surviving. As we handled our missing data, we found something interesting. The missing data itself was telling us a story about each patient. For example, if a patient arrived with a stopped heart, the doctor and nurses are unlikely to record a heart rate. With this knowledge, we were able to turn that missing data into a narrative to provide to our models, identifying the state of the patient throughout their time in the ICU. Now that we've gone over how we got the data and prepared it, I'm going to pass over to Ravinder to share in our exploration of the data. Take it away, Ravinder.
Thank you, Shay. Before we start exploring data, it would be helpful to have a high-level picture of the process here. I have 2 blocks here. At the top, you can see the course a patient takes from hospital admission to the final outcome. That is, after the ICU course, either patients recover or maybe doctors could not save the patient. What we are trying to do is to predict the outcome based on the data from the first 24 hours of ICU admission. How do we do it? First, we have to identify the variables and predictors that have an effect on the outcome. We started with the very obvious ones. For example, how old is the patient? Do they have any underlying conditions? How are his vital signs? We explored these variables to see if they impact the outcome, and the chart on the left shows that they indeed do. The survival rate is lower for the patients who have underlying disease versus those who do not. We use these variables, predictors, as the input to our model. And the chart on the right shows that the results we got are comparable to the baseline, which is the existing model used by the hospitals. So how do we improve our model? The next thing our team did was to talk to MDs, nurses, and ICU techs to better understand the data and dive deeper into the human physiology. Diving deeper, we started to explore other important physiological markers which are more relevant to the patient in ICU. For example, pH level, lactate level, blood urea or nitrogen level, oxygen saturation, and so on, to identify better predictors. As you can see in the charts here, although there is a considerable overlap between the values for the patients who survived versus who did not, there is still some separation and the outliers which can serve as better predictors. One more useful thing we did was to combine different variables to create more insightful features. For example, we tried to identify most critical patients by looking at those biological features which provide insight into their condition. A low pH level, high lactate levels indicate that the patient is very close to that thin line which separates life and death. Additionally, we try to make a new variable which is based on perception of the medical staff about the patient condition. That is, which tests were run, which tests were not run because they thought they were not needed. And these new features turned out to be pretty useful for modeling, and now Alan is going to talk about that part.
Thank you, Ravinder. Now we're going to talk about how we measure our predictions. We have a very small portion of positive cases, and the cost of a wrong prediction is critical. In order to reduce the overlap of positive and negative cases, we use the scoring system naming ROC-AUC score. As you can see, the graph on the left, the red and blue bumps are the distribution of positive and negative cases. The less the overlapping of the positive and negative cases, the more the curve going to the up left corner of the graph on the right side, which indicates a better prediction. With the awesome work our team did in creating some new measurements, we managed to use different algorithms to build our model and gradually increase the performance as shown on the chart on the left. The baseline model is the original Apache scoring, which is 84%. Our best model on the far right bar increased the score on the all of sample data set by 7% and reached 91%. What does this 7% mean? Our model reduced the number of wrong predictions by 1,623 cases over the original Apache score system. Not only do we want to make better predictions, but also we want to know what are the key drivers to make those predictions. We have discovered some of the most important vital signs which in the future doctors could use as a quick tool to screen patients. As you can see, the top 10 vital signs are listed on the graph. The 3 highlighted vital signs are the ones we created. Now here's the question. How do doctors in the future apply the knowledge our model produces? The model we used is a tree-based model. It looks at the current vital sign, then based on the order of the vital sign importance, it determines the probability of an outcome or moves to the next vital sign. For example, our model first used a critical condition vital sign, and based on the values, it moved to the next level. And to see whether the patient has either a cardiac arrest or brain hemorrhage. Then based on data from those conditions, our model determines whether the patient is going to survive or move on the evaluation of other vital signs to further determine the outcomes. Now Chase is going to cover some insights and recommendations.
Thanks, Yipeng. Now, what can be done with the work our team has produced? First, like he said, we need to go a step beyond just better predictions. Our model can provide a per-patient risk assessment, giving physicians and clinicians the ability to visualize underlying risk factors for patients and better analyze where they're headed. As Ravinder mentioned, in our conversations with hospital stakeholders, ER techs, and doctors, we spoke with them about the identification of 2 key patient groups. The first is obvious, the high-risk patients. But that second group, we can utilize our model to identify unexpected outcomes where patients had a negative expected outcome, but they recovered, or the opposite. This would give them an opportunity to assess each case to improve the outcomes of the possible patients regarding recovery, as well as possible mitigations on the negative ones. And as Shay mentioned, the data originated in an open source fashion from MIT. So in the same way, we invite you to take a deeper dive into our data using the website that we created. There, you'll find this deck with an accompanied appendix with all the tools and data science techniques we used. You'll find the recording of this presentation and a more in-depth one if you're into that extended cut version. Also, you'll see interactive charts so you can explore the data yourself, a link to the project GitHub so you can review our code, and more. We invite you to do all of this because a project like this matters. Once again, from all of us, thank you for your time. And please let us know if you have any questions.